What happens if you take the spectrum of an individual star? Well, you're going to get an absorption spectrum, much like this one taken by myself not too long ago, so a little casual flex there. The absorption spectrum is seen in the blackbody curve of any star, and at the core of every star is the process of nuclear fusion, which powers its radiation. Some of that radiation gets absorbed by the outer layers of the star, creating absorption features like the one that you see right here, which is the famous H-alpha absorption line at 656.3 nanometers or 6,563 angstroms for the astrophysicists in the crowd. So now the question becomes, what happens if we take the spectrum of an ensemble of stars rather than just one individual point source? And here's an example of an elliptical galaxy spectrum. And if you compare it to the spectrum of a single K-type star, so a small, cool, red-type star, you'll notice a lot of similarities. However, the overall shape of these absorption features is actually going to change a little bit due to the motions of all of these stars in the object. So some of the stars are going to be blue shifted because they're going to be moving towards you, and some of the stars are going to be moving away from you and be red shifted. And that random distribution of radial velocities is going to be described by something called the Maxwell-Boltzmann distribution, which is effectively a Gaussian. What this random motion does is it creates every single absorption feature from every single constituent in the ensemble is going to be a little blue shifted or a little red shifted. When you add all of those up, that's the spectrum that you actually get when you take a spectrum of one of these objects. And so what happens is we add up the spectrum of each individual constituent in the ensemble, creating the absorption feature that you see when you actually take the spectrum of the ensemble. And what happens is the shape of each absorption feature gets a little fatter and a little stouter. This is an example of the Gaussian type profile that you would apply to an absorption feature if you wanted to model it. The full width at half maximum is what we use to determine whether or not an absorption feature has actually experienced what we call Doppler broadening, which is just that phenomenon just described of a little bit of blue shift, a little bit of red shift, all being superimposed on itself to kind of widen and fatten out these Gaussians. The sigma in the equation on the right, which you could see better if I moved my face, is the velocity dispersion of the ensemble. The velocity dispersion is just a number typically reported in kilometers per second, and it is the velocity of a particle with the mean kinetic energy of the ensemble. If you model an absorption feature with this equation, the sigma value just pops out. So that's one way of finding the velocity dispersion of an ensemble. In practice, there's another way. This is an example from Solveig Thomson's master's thesis. If you're in the astrophysics or physics program at the University of Calgary, you're probably familiar with Thomson's name. Instead of modeling each individual absorption feature of a spectrum that she got, she instead used the technique of stellar templates. Stellar templates are effectively numerical models that you can build with computer code. You can play God, and you can create any population of stars that you like. And because you know the properties of those stars, you also know the velocity dispersion of that population. And so if you keep iterating and create a variety of these populations, you can then fit them to the data that you get using a variety of common curve fitting techniques and error bootstrapping protocols that are kind of outside the scope of a typical undergrad statistical mechanics class. But here we can see how she's taken the spectrum at different radial distances from the center of ultra-compact dwarf galaxies. And we can see that as we get further away from the center of an ultra-compact dwarf, the velocity dispersion actually goes up. So the stars that are further away from the center, on average, are actually moving faster than the stars towards the center. Now, she got this data using the NIRSpec plus IFU, the Near Infrared Spectrometer and Integrated Field Unit, which is a very, very cool spectrograph on the James Webb Space Telescope. It almost works like a camera, but for spectroscopy. So with a normal camera, you would get light recorded in each individual pixel. With NIRSpec plus IFU, you get a spectrum for each individual pixel. You can apply the technique that I just described to get the velocity dispersion of the spectrum from that pixel, and then you can create what's called a velocity dispersion map like this, which shows the exact same trend that we just saw from the previous figure. The stars further away from the center are moving a little bit faster. Now, the question is, how do you actually get the mass of if there is a black hole at the center of one of these compact systems? And what you're going to do is you're going to use the virial theorem as seen in astrophysics classes, not the virial theorem that you'd get if you're in a statistical mechanics course. This is more the astrophysicist version. And the kinetic energy is described almost like classical kinetic energy, but you replace the velocity with the velocity dispersion. And then the potential energy is something that's a little bit interesting. You kind of have a choice. You get to choose what gravitational potential you want based on the object that you're trying to model. If you're looking for the black hole at the center of one of these compact stellar systems, you would choose a model like that. The one that comes to my mind is the NFW model, which we analyze in Astrophysics 401, Galactic Astrophysics. And then you can get the potential energy from that, plug it into the virial theorem, and solve for the mass. That's one way of finding or really estimating the mass of the black hole at the center of one of these compact stellar systems. And that is how you use the magic of Maxwell-Boltzmann mechanics and distributions to probe the kinematics of distant compact stellar systems in search of intermediate and supermassive black holes in hopefully less than 5 minutes. You're welcome.